So this is page 112. Says the average length of jury trial in Colorado is known to be 440 minutes. The state of Colorado changes the law on jury trials. Will these changes affect the average length of time? All right. Says the first 100 trials are used to study whether this law will have an effect on the average jury trial time. The average of those is 100 trials for 426 minutes with standard deviation 64. All right. So I think we can do this. So problem 1, our null and our alternative. So our null jury is equal to 440. And then jury is less than 440 because they got that 426. So I definitely have a direction on this one. Yep. Here comes the...
Sure. Wouldn't the alternate though be not equal to 440 because we don't know that pre-experiment? I know you're not. So
Flip back page. Early on. We're doing the two. Let's just think that as a rough estimate.
you don't know that until you actually do the experiment.
That's right. That's right. All right. So, because this is a two-tail situation, I'm going to change these. So, let's see. Because we're doing two-tail, we're going to go not equal to and equal to. Go with that?
Oh, if it's two-tailed?
Yeah, because I forgot this was the two-tail.
Okay.
All right. So, not equal to. Actually, I got to flip-flop this. Not equal to and equal to. It's like, sure, make up your mind. Sorry, guys. All right. Check the assumptions. So, I guess this is number 8. Number 9, check the assumptions. So, friends, they do 100 of the first trials to check. Okay, there's no random. That's kind of a bad thing. That's kind of, we have to watch out for that. It says create a null hypothesis sample distribution and p-distribution. Okay, so for number 10, create ourselves a normal distribution best we can. We're going to go 440 here. And we have to figure out our standard error. Yeah. Why not? You don't have... Because it's 112. What's there's one right before that. Oh, okay. Good thing I'm recording. We'll figure it out. All right. I need to find the standard error. So we have what we have. Standard deviation 64 over the square root of the sample, which is 100. So that's going to be 6.4. So then we got 446.4. 0.8, 612, carry the 1. That's 5, 452. And then go one more out here. 12, carry the 1, 6, 8, 9, 459. I need a calculator because I can't do arithmetic this early in this morning. Jeremy think I could. 440 minus 6.4. So going this way, 433.6 minus 6.4, 427.2. 420.8. All right. Are we good? All right. So it says calculate the p-value based on this? Well, we had this 426 minutes, right? Which is like here. Okay, so that's like your 426. But remember, it's a two-sample distribution, so I'm going to go 440 minus 426, so the distance there is 20. So this will be like 460. Okay. All right. And then it says using the alpha value of 0.05, explain the appropriate decision in this context. Okay. All right. So if we're going to use 0.05, but it's two-tailed, what should we use? What should be our breaking point?
0.1.
Yeah, 0.1. Okay. So we're picking an alpha value. We're going ahead and saying, hey, we're going to say alpha is 0.05, but because it's two-tail, we're actually going to test alpha at 0.10. Okay? All right. Desmos time. Let's have some fun. All right. So normal distribution, 440, comma, forgot. 6.4. Thank you. Then we're looking for 26. 6.4. And we just have to pick one of the directions. Okay, what? Bounds area? Wait a minute. Yeah, I don't know. I don't know what's going on here. What's... Shh. Okay, does anyone... Cumulative probability. Where did I... How did I switch that? That's not it. Where is my... did something change on Desmos? Do you guys still have the little dots below? Yeah, you do? Or I don't know where this came from. All right. Negative infinity. All right, we can do this. What am I testing against? 426? All right. So we're going to get, I don't know why mine looks different, but we'll go with it. So we're going to go 0.014. And we have to multiply that times 2 because it's two sample. So we're looking at 0.028 is our p-value. All right. Is 0.028, is that smaller than 0.10? And the answer is smaller. So reject the null. Yeah. Right? Did I do it right? 426, right? Oops, get rid of this. Yeah, we have to find one of the tails, then we have to double it. So I came out with, once I doubled it, p equals 0.028. So reject the null, strong evidence. Against the 440 minutes. But the big thing that sticks out on this one is we do have we selected 100 cases. They were not random. They were just first 100 cases. Let's see. Explain why this is a two-tail hypothesis test. Okay. So we're wondering if there was a difference in the court time, so that's why it would be a two-tail test. We're looking for some sort of, change in number to the 440. That's 13. Which type of error is plausible here? So type 1 is we reject the null when it's really true. I think so. All right. So this is a type 1. Type 1 error, reject the null when it's really true. Something like that?
Wait,
Yeah.
we rejected the null, right?
We did.
But the null is, the jury is not equal to 440, so wouldn't there be strong evidence suggesting that it is 440?
Well, we're just rejecting the 440. We're not saying that 440 is the pivotal amount.
Okay.
13. It's a two-tail test because we want to see if there's a difference in the court time because of the new policy.
So what did you get for 13 and 14 again?
You what?
What was 13?
13, what does it say?
Explain why it's a two-tail.
Because we're looking to see if there's a difference in court times with the new stuff in place.
Okay.
14, it's a type 1 error. We could have a type 1 error when we rejected the null when it's really true. All right. So, did the no-namers find a place to live? If you are one of those no-namers, make sure you hand it in. Make sure your name is at the top of this so I can get you points for it. All right. So, again, my friends, on page 41, what do we do if we only know the sample standard deviation? Because every time you take a sample, you're going to be able to find the standard deviation of that sample. So you're kind of in a moving target. Agree? So if this was a sample 1, and then sample 2, and let's say this all has all this randomness that goes with it. So the mean of our samples could all be a little bit different, and our standard deviation of all of our samples could also be all a little bit different. So it's like, how do you know if you're actually doing this correctly? Well, you use a t-distribution, a t-test. Okay? I mean, it should be obvious. Like t, you're in trouble if you only know the sample standard deviation. All right. So the sampling distribution of a sample has a mean of mu and a standard error of theta or phi over square of the sample standard deviation. Notice standard error requires us to know exactly what the population standard deviation is. In most cases, we have no way of knowing the population standard deviation. Okay, so that's your whole parameter standard deviation. So consider a situation when we wish to know the average cholesterol level of American adults is greater than 200. We wish to use a sample of 1,000 adults. Nonetheless, the standard error formula insists that we know the population standard deviation. That is the standard deviation we would obtain if we had everyone's cholesterol level in the entire nation. Okay, so we don't know what the standard deviation is of the entire population of the nation of the United States, but we do know from our sample of 1,000 randomly selected people, we know their standard deviation. Okay? Researchers often have no chance whatsoever of knowing the population standard deviation, so the formula doesn't work up above. Okay? It becomes an unknown. However, we can use the standard deviation and estimate the population standard deviation. This is problematic though, because we are likely to be off somewhat. This creates uncertainty, and the normal distribution doesn't apply with this extra level of uncertainty. There's a different distribution called the t-distribution that looks very much like a normal distribution, but factors in the extra uncertainty of the sample. Okay? So, you're going to use a t-distribution. You're going to use a t-distribution if you know your sample standard deviation. Okay? Now, I pulled up different. Let's see if Chrome works better with Desmos for right now. All right. Let's see what happens here. Oh, it's slower. All right. So, yeah. All right. It's still doing that. All right. So, normal distribution, t-distribution. T-distribution, they're asking for degrees of freedom, so let's just say it's 10 for right now. All right. So, friends, actually, let's change our t-distribution to a little bit smaller. Let's go to 5. All right. So, take a look. I have two very similar looking things up there, but they're a little bit different. I have the red, which is the normal distribution, and I have the blue, which is a t-distribution. A t-distribution curve looks very similar to a normal distribution, but you notice it's a little bit shorter, and as you go out to the edges, it follows the asymptotic rule to the x-axis, the same as the normal curve, but you still have these areas. So there's a smidge of error. Okay, so now let's explain what a normal distribution is. Normal distribution is you have a standard deviation that comes with it. You have a certain distance one way or the other from your mean. A t-distribution takes into account that you might not know the standard deviation of the entire population, but you know it of the sample you took. Okay, as your t-distribution sample gets larger and larger and larger, the closer and closer and closer it gets to being right on top of the red line. So if I made this say 100, so friends, I'm not an artist, but if I'm going back and forth between these, notice blue, red. Do they look the same? So as my sample size gets larger and larger and larger, the closer and closer and closer our t-distribution becomes to a normal distribution. Okay? For a one mean t-test, the degrees of freedom is simply one less than the sample size. So degrees of freedom, if I have a sample of 20, degrees of freedom you plug in, 19. If I have a sample size of 100, my degrees of freedom is one less than 100, which is 99. If I have a sample size of 2, my degrees of freedom means my sample size is 1. So if you do a sample size of 1, take a look. Degrees of freedom on this. It still looks like a normal distribution. You can definitely say that it's way underneath it, but it's still kind of a shaped curve like that. It's symmetric. So the shape of a t-distribution somewhat changes with the different degrees of freedom. So the higher your sample, the closer and closer and closer it gets. If you go to the next page, they're doing up at the top, on page 42, they're doing up at the top what we just had done, okay? So you have the normal distribution and then degrees of freedom of 20, degrees of freedom of 10, it gets lower. As you can see, the degrees of freedom increase, the middle of the bell shape gets taller, sides get shorter. When the degrees of freedom is very large, the t-distribution becomes indistinguishable from the normal distribution. For this reason, some statisticians argue that either a z-test or a t-test is appropriate with large sample sizes. If we have a calculator, so the next thing is we're not using the graphic calculator, we're using Desmos. So it's going to work very nicely for us. Of course, when it asks for your calculator commands on a test or quiz, normally just an answer works just fine because Desmos provided it for you. All right, so let's take a look at this example. What percentage of the t-distribution with 27 degrees of freedom is greater than 2.3 standard deviations above the mean? So what you have to realize is the standard deviations are the z-scores, which are the x-axis. Okay? So let's get away from this. Let's change this to, we have 27 degrees of freedom. I don't know if I got an update or something, but I'll tell you what. So we want greater than what? Greater than 2.3 standard deviations. 2.3 to infinity. All right, so in this case, we come up with 0.015. We have in our thing is 0.0147. So this one was a little bit closer. So we have basically 1.5% of our area under the curves over here. One example of the t-distribution with 16 degrees of freedom is between 1.5 and 2.5 standard deviations. So all you have to do is you're not plugging in the mean and the standard deviation, you're just doing the degrees of freedom. So the second example, they say you have 16 degrees of freedom. So that means you have a sample size of 16 or 17, and we want between 1.5 and 2. Bless you. Bless you. Whoops. What percent is between, oh, below. That should be a negative. Shame on me. Negative. There we go. All right. So if we do this, that's basically showing the difference between negative 1.5 standard deviations to 2.5 standard deviations, which are accounting for roughly 91.2% of the area in the curve. You'll notice the t-distribution function uses z-scores, actually t-scores in this case. Okay, so if we're using a t-distribution, if this is not a normal distribution, these are no longer z-scores. Z-score is the same thing as a standard deviation with decimals. Okay, we're using a t-score, which is down here. A t-score, as your sample gets larger and larger and larger, the sample standard deviation, or the standard deviation becomes very close to the z-score, which you don't notice a difference. All right. So that's what I have. Let's take a look at what the assignment says, so we can maybe knock a little bit out. All right. Let's see how I taught. How you can start answering some of these. This is on page 113. We're starting the homework a little bit. It says, which t-distribution looks like a normal distribution? One with degrees of freedom of 40 or 1 degree of freedom of 60? Which one's going to be closer to normal, 40 or 60? 60. The larger your degrees of freedom, the closer it is to a normal distribution. Which t-distribution shows a peak in the middle of the bell shape, degrees of freedom of 5 or degrees of freedom of 20? So as the degrees of freedom get higher and higher this actually approaches to the normal. So if you change your degrees of freedom of 5 is going to be a little bit short underneath the normal curve, whereas 20 is going to be above it because we are approaching the normal distribution once we get into larger numbers. Which t-distribution shows higher at the far left, far right ends? So if you ever get stuck on these, like, Stirrup, I can't make these work in my head because, I've looked at other things, just do this. So let's not even worry about that. All right, so if we did degrees of freedom of 5, and then I did a t-distribution, 5 versus 20, so 20 is taller, okay? If I did degrees of freedom of 20 to 25, if I do 25, this should be a little bit taller. Ooh, it's getting close, so we actually have to zoom in on it. If you zoom in on it, on a normal curve, you can see that the degrees of freedom of 25 is a little bit taller than the degrees of freedom of 20. Again, as your degrees of freedom get larger and larger, degrees of freedom being 1 less than your sample size, and more and more and more. All right, so 4, 5, 6, you're just looking as the t-distribution on decimals, plugging it in, so it should be pretty simple. 7, 8, 9, 10, these are all the same. All right, so my plan for this week is we'll have something each day. We will actually have a quiz on Monday. It will be the last quiz of the unit. because I'm not going to be here. I'm giving you that quiz. So you get to work on it together like always. And then on Tuesday, we'll review. Wednesday, we'll review. Thursday, we'll do our test on this chapter. And then Friday next week is the infamous Orange story, which is the Super Bowl of my stories. I think you'll enjoy it.